Now let's talk about a Lie derivative. We'll first define Lie derivative and then we'll state some properties of it. So first, let's say I have two flows on a manifold and we're calling them as sigma and tau, be two flows generated by the vector fields x and y respectively, such that we'll have the equations, the differential equation that governs the flow, it should be x. Yeah. So what we have essentially is that if we have a manifold like this, let's say, and let's say these blue lines are the flow or flows, these flows are generated by x, and the yellow lines are the flow generated by the vector field y. Okay, so what we want to do is that we want to compute the change of the vector field y along the flow direction of x. So if I write it down, our goal is to compute the change of vector field y along the flow direction of x, and we denoted this as this symbol. This means you are trying to compute the change of the vector field y along the direction x, and this L means the Lie derivative, and we will define this in a few seconds. But first let us talk about the machinery that we'll need. So now I'll draw this picture again, but in a simplified manner, where I will get rid of this M and I will only represent these lines. So noted the flow generated by x as the blue thing, right, and the flow generated by y as the yellow thing. So the flow generated y, let's call it this, let's call it this, let's say this is tau of tx, this is tau of tx prime, and since we want to compare two tangent vectors, but we want to compare it along the direction of x, so we'll need to draw the flow generated by vector field x, which is the blue line, and let's say this is the point x, this is the point x prime, and the tangent vectors along this flow, let's say this is 1, and we are calling it, let's say, y of x. That means a vector, or the vector component, however you want to call it. And at this point there is another tangent vector like this. Okay, and note that the distance between point x and x prime is infinitesimal. So let me make a brief comment that x prime is a nearby point of x such that this x prime is denoted by this flow, because again recall that these blue lines were generated by x, which was just a the flow, and the flow was given by sigma, right? So this is just this. What it means is that x prime is just, let's say, x prime of mu. If you want to go to local coordinates or in terms of local charts, this will look something like this. Okay, this is what x prime is. Now what you do understand over here is that these two vectors are at different points, so we cannot subtract them yet, because if two vectors are at a different point, we cannot bring their, let's say, tip to the common to some common point, sorry, the base to the common point, and then we cannot subtract it because they are on different points. If we had both of them at the same point, then we could define a subtraction. But this can be done. We can actually compare these two vectors, and the idea is to use the push forward mapping. That means you push forward the vector on point x prime to this point x, a push forward, and you can easily figure out what that push forward mapping is. This push forward mapping is nothing but going back to this on the negative epsilon parameter. That means if you want to go from x to x prime, you need to use this mapping, right? This one. And if you want to go back from x prime to x, you need to do x mu minus epsilon x of mu, this one. So if you do that, then you can project this vector over here onto this point, and then you can compute the difference. Okay, so this is the idea behind this linear derivative thing. So let us now formally define it. L of x y is defined as the following. We have this limit epsilon goes to 0, 1 by epsilon, and we want to have this sigma minus epsilon acting on my vector y at this point x prime, which we denoted by sigma epsilon of x. That means this infinitesimal transformation will carry me from x to x prime, okay, minus the vector on point x. Now it's just a matter of computation. Again, recall that y can be written as y mu del x del mu in terms of the local coordinates, that is, and this is x mu del x del mu. And one thing to note is that previously we were talking about these push forwards and pullbacks for two different manifolds, right? Because we said that if I have some sort of a mapping from one manifold to another, then I can have this push forward thing that will take me from tangent space of one manifold to the tangent space of the other manifold on some point f of p, right? But in our case, n is just equals to m in this case. Okay, so this is completely valid. And now for the computation. So let's try to compute this part first, and then we will compute the other part. Since there is a push forward mapping, this is the push forward again, and remember that push forward acts on vectors and pull back is on the forms. So Even though you might think that you are pulling things back over here, it's not. You are just pushing them forward in the negative direction. Okay. So the first things first, we have to compute this quantity. The y sigma y at this point x prime, which is again very easy to compute, is just y mu. But now the point is not just x, right? Because what does this sigma does from x? It takes you from x to x prime, which was just x plus epsilon capital X. And if you give the components, it looks like this. Okay. So now this is y, the component of the vector y, but at a point this. And you can have the basis vector. For now, we are denoting the basis vector like this, let's say, so that we won't make a mess of notations, so that it doesn't look very ugly. So let me write it as E mu. Okay. And now we have to do this. That means we have to take the push forward of this guy over here. The push forward of y and this. And note that when you write it like this, you are actually evaluating it x plus epsilon x. I got rid of the indices just for convenience. Okay. So if you recall from the idea of push forwards, that the f star v, where f star was the push forward, v acting on g, where g is some function, was the same thing as v acting on the functional composition, like this, right? So essentially what we can do is that we can use this expression to simplify our computations. And when we did this push forward things, we took g as a coordinate function, since this is true for any g function that you take. So what we essentially got is that this quantity is nothing but v mu del f del mu. This one, right? Here we will face the same thing. But first, you can see that here you can make a Taylor expansion as well, because this epsilon is a small parameter. So let's be done with that first. So again, I write this. Let's call it mu. Did I use a new? Oh, sorry, it should be a new. It really doesn't matter, it's up to you. I'm just keeping this difference a new coordinate, but eventually it will spit out some y mu, because there's a summation over that as well. So in the argument, we're just using a different index to label, and we're trying not to confuse ourselves. Again, I'm not writing the points again, because that is understandable what we're doing. And if you take a Taylor expansion of this right now, you can just get rid of these indices. and you want to have a first derivative like this, e mu, and I ignored all the higher order terms over here, the higher order terms in epsilon. Okay, and this is a first order Taylor expansion of this guy. Okay, now to compute the quantity this on y. Again, this can be thought of as that f star thing, right? And this can be thought of that v thing that we talked over here, and it was just this. Oh, sorry about that. I should denote it with the star. Yeah. To understand, to make it clear that this is a mapping on the tangent space. Yeah, there should be a star. So if I do that and I use this expression over here, then this is just this component and the derivative of the explicit form of this sigma minus epsilon mapping, right? So let me write that as y mu x, because you can see that if you just write it like some y prime mu e mu, this is the component, right? So that's what I'm writing over here. This is y mu epsilon. Let's give it a, oops, there should be a new index over here. Yeah, it should be a new, because the powers, the 1 2 3, all of this has to match, so this has to be a new. Sorry about that. So this is epsilon. Let's call this another new index. Again, it really doesn't matter, you can even write ABC as long as you understand what you're doing. So this is lambda y mu. Okay, then we have to take a partial derivative of the function itself. That is, we have to take the partial derivative of f of minus this, right? And this sigma minus epsilon, I got rid of these points and all that stuff to make things cleaner, but if you can recall that it was just nothing but, let's say, x mu minus epsilon capital X mu, like this. Okay, and when you are doing this, you are actually coming back to point x. So some people would even write it like this, that this vector over here that we evaluated, it was at some x plus epsilon x, but after you use this push forward, you return to point x, right? So let's use this thing on this expression. So what we have right now is y mu of x epsilon capital X of lambda partial derivative y mu, then partial derivative of, oh yes, I missed the basis vector. Now let's write it like this, x nu minus epsilon x of nu, and all these quantities are evaluated at x. I'll just denote it with this sign over here, and here you have the basis. So this is y mu plus epsilon x of lambda del of lambda y of mu, and this partial derivative is with respect to x mu, so you will have a delta nu mu minus epsilon del mu x of nu, and then have the basis, which is again is nothing but this thing. Okay, so we already computed this thing at a point x, right? And now let's call this equation number 1, and we have to do the following. We have to subtract the vector that was originally at point x from 1, right? And that was just what? This y of x can be written as some y mu e mu, right? So we just have to subtract it from 1, and let's try to do that. So if we do it, this is just obviously you can simplify this even further. You can take 1 and simplify it even further. So let me do that explicitly. Obviously all these calculations are carried out at point x, so there is no need to write that over here every time, as long as you understand. Let's say y nu e nu. We're doing it so that we can factor out these bases. Since they are dummy variables, it really doesn't matter. So let's simplify the first term over here, and again we will ignore all the higher order epsilon terms, even though if you want to keep them, if you want to apply the limit when epsilon will go to 0 and multiply this quantity by 1 upon epsilon, all those higher order terms will go to 0 anyways. So we are going to skip them from this step onwards. So this is just y mu delta nu mu minus epsilon y mu partial this, then we have this epsilon term, epsilon x lambda del lambda y mu. I have a del nu mu, and then there is order epsilon terms, and finally y nu, and all of this we can take out these bases as a common thing or a factor. This is easily understandable. This y mu delta nu mu is just y nu, right? So let's write y nu directly. Y nu, these two terms cancel each other out. All the order epsilon square terms are gone from the calculation. So if I factor out this epsilon, what I have is x lambda del lambda of y of mu. Oh yes, there is another delta over here, so this will make this mu as nu, so it should be nu. And then I have this term minus y mu del mu x of nu, right? Now let's call this equation 2. Recall the free derivative of y along the flow of x was defined as limit of epsilon goes to 0, 1 by epsilon, then sigma minus epsilon, which is a push forward of y on point x, then y of x, like this. So we computed this quantity. We just use the result from equation number 2. We have epsilon goes to 0, 1 by epsilon times epsilon x lambda del lambda y of nu. Oh yes, there should be a e of nu as well. the basis. Forgot to write that. Yep. Minus y of mu del mu x of mu. And you can even change this lambda to mu if you want. It's a dummy index, it really doesn't matter. Or you can change these mu's to lambdas. So these two cancel each other out, the limit goes away. So if I take this substitution, lambda goes to mu. This is just x mu del lambda y mu minus, sorry, it shouldn't be lambda, it should be mu. Yeah. And then I have y mu del mu x of mu. This is my Lie derivative of y with respect to x along this is my Lie derivative of y along the direction of the flow of the vector field x. Again, E nu is just this guy. Okay, and you can even see that this derivative, this Lie derivative, is also a vector field. Vector field, where this is the component. Geometrically, what this means is that geometrically this Lie derivative gives you the failure of the parallelogram in this manifold. And what I mean by that is that it actually computes by how much the parallelogram is not closed. Okay, that's what the geometric meaning of this Lie derivative is. And you can even show that this Lie derivative is the same thing as the Lie bracket. So one can even show that the Lie derivative is the same thing as the Lie bracket that you know as a commutator. Lie bracket. That means if you want to compute the change of y along the flow of x, you can just take this commutator and be done with it, where x and y, they are both vector fields. Okay, you can also show that it satisfies the Jacobi identity, the skew symmetric properties, and bilinearity properties. So this is a very useful tool when you want to do some general relativity. You will see some applications of this thing, but for us only the definition and some of showing that some of the properties that it satisfies will suffice. And before I finish off, I want to make a brief comment about the Lie derivative of forms. So this is a comment. We defined Lie derivative for vector fields, but we can also define Lie derivative of a one form along some vector field. So just like we defined Lxy, we can define Lie derivative of a one form, let's say this one form is omega, along the vector field x as following. L of x of omega will be defined by just, it's almost the same thing, but this time instead of a push forward, since you are dealing with a form, you need to use a pull back. And this time notice that you are not pulling it on the opposite direction, rather you are making the form go in the forward direction. And you can do a similar analysis which will lead to a similar to the following expression. And this almost looks like an anti-commutator, but we are not going to say that this is indeed an anti-commutator because you actually need to show that. So this is your Lie derivative of a form. And now you may ask, okay, so I can take Lie derivatives on vectors, I can take Lie derivatives on forms. What about scalar functions? Because in some sense you can think of it, this Lie derivative, you can almost draw close analogy between the directional derivative, right? Because you are measuring the change of one thing in some direction. So let's see what happens when we act the Lie derivative on some scalar function f. Okay, so if I do that and I use the definition of the Lie derivative, then this is just f of, since this is a scalar function, there is no trouble of push forward and pullbacks and those stuffs. So this is just at a point x prime, which is denoted by this sigma epsilon of x, that it is starting from x and going to some point x plus epsilon, then the component of the vector field minus the function originally we started to work with from point x. So then let's try to see what this gives us. If I write down it in the component form, x mu epsilon capital X mu minus f of x mu, right? Then what I can do, I can take this function and Taylor expand it. If I do that, I'll have this, then I'll have my vector field at some point x, because we are expanding around x mu plus epsilon x mu equals to 0. Okay, so there will be a partial derivative of f with respect to x mu, and then there will be my parameter, and then there will be higher order terms, then minus f of x mu, right? These two cancel each other out. Higher order terms go to 0 when I multiply this with this 1 by epsilon thing. So this will cancel this one, the limit goes away, and I'm left with this thing only. But this is what? This is just the directional derivative. So when you apply this Lie derivative onto scalar functions, you get the directional derivative. So this will be all that we'll have to say about Lie derivatives. For now.